So Dr. Narn, quick
Hmm.
question on like the quiz. Are you planning to like adjust the grades for that?
Yeah, I'm
Due to
gonna do
the
that.
issue? Okay.
Uh, I have been, let's see, resume. Okay, all right. Exams on Thursday. I still haven't decided to do a take-home portion, and the reason is I think some of you still have problems running Python or running OD or SciPy.integrate on your computers. And I think I found one person having a problem after the homework solution was posted. So that person, or he's not alone. I think many people didn't do the homework. There's only 28 submissions or something like that. So, and then I think that many of you may try to take the code and put it now in Python and find that Python cannot find OD integrator. One student was able to solve this, but I don't think it's a solution that's really easy for everyone to follow. And that person happened to know Python a little bit more than the average undergrad. Um, so you need to let me know by tonight or tomorrow morning. Otherwise, I am not going to do a take-home portion because I don't want people to email me tomorrow night and say Python doesn't work.
So
Okay.
the take-home portion would be, like you said, 36 hours before the exam?
Well, yeah, it would. Well, it would be, let's say, 24. Sorry, not 36, because I would have to post it tomorrow morning, like at 3
Okay,
a.m.
so 24, so like 3 p.m. tomorrow is when it would happen.
Yeah. So I need people to let me know because I know at least one of you has problems. So, and my feeling at the moment is that I'm not going to do a take home portion for the exam 3, but I will do one for exam 4 because there's no way to not do one. There is a way not to do one for exam 3, and that's fine. It's not going to make the exam harder. It's just going to switch my um, it's just going to switch my priorities, which is why another reason why I'm going through this review today so that it could be more clear what you expect to know and how you expect to solve problems.
So if there was no take-home portion, would you still use Python on the exam, or you would just kind of
No, no. So say that again. If there was a take home portion,
oh, like if there is no take-home portion, then
no, you will not use Python on the exam. What you will be asked to do is to set up a problem as you would with all the info that you would need before you plug it into some kind of solver.
okay.
Then I would give you the solution to that problem and I will tell you to do certain things with it. So saying that if you set this up correctly, and it's going to guide you through, it's not going to be random. It's going to guide you through, which would make it a little bit straightforward because it's going to follow the algorithm, right? I'm going to ask you, write the mole balance. What is the net rate? What is the concentration in terms of blah, blah, blah? Maybe it's in terms of molar flow rate and something like that. Um, and what are I'm going to ask you to evaluate your initial conditions. For example, if it's a gas phase problem, but you have a CA naught in your rate expression, after you've derived the rate expression, you need to calculate CA naught, and that's an actual algebraic equation. Normally you'd be using the ideal gas law, for example, but that's how you would do it. So that's how I'm going to set it up. One of the problems so that when you get to a point, it's going to say, okay, you're going to write all your algebraic expressions, all your initial conditions, and all your um, differential equations. And this is how you would basically plug it in. And that should give you, the answer if you input everything correctly, essentially. So it's a good question to be. The answer to that is yes. I don't know how useful they're going to be because the homework was very, what's the word? Substantive and covered everything. I will post probably 3 problems with answers, but that it should help, I think, but it's not going to be extra released because the homework really covered most of the things you need to know. Yeah, so just for you to see a past exam problem, really, or 2. Yeah, this exam is significantly easier than the second one. You should know that as well. And it's of course the easiest one was the first one, but this one is easier. It's significantly easier than the second. Okay, now let's do a review. Let me open up my Scribble. So I'll try not to say, but we may end up early. But I'm gonna try not to say. I always jinx myself whenever I say that.
Also, just real quick, as a tip for anyone that might not have their like Python on their computer working, you can go to like collab.research.google.com, and it's basically an online Python like scripting service that it's like free and you can like run your stuff. I'm not sure if it'll work for everyone, but it might just be something for someone to try if they're having some troubles on their actual computer.
Yeah, I've been using that too, and it works pretty well.
Yep.
Ah, that's nice. But I still may end up not doing a take-home portion because that's an outside resource and just seems like it could be too much of a headache if it doesn't work for somebody. But yeah, I think that will be best. And it also makes grading the exam easier if I don't have a take-home portion.
Do you
And
know if
faster.
we're going to have to code like the stage stepping that we learned the other class?
To code that,
like you said, you could either use Excel or Python. to do
well,
the
if
reactor
I give a problem with reactor staging, it will be graphical. So you'd basically take a ruler if I do that, but I'm inclined not to. I don't know. I'm not for sure. I'm not sure. And you can basically take a ruler and then look at the number, right? It's going to be graphed for you.
Okay.
It's not going to be that you have to do solver on Excel to equate the equilibrium conversion with the adiabatic conversion.
Now, this is I don't know. When I was thinking about it, I just got confused. How do we know the slope of the line between the like the actual graph section and then the temperature, like the T naught and the T? How do you know the slope to find
The
that?
slope is your, we're going to get to that today, but the slope is your adiabatic temperature. So it is, for example, FA naught times delta HR divided by the sum of the flows at the inlet times heat capacity.
Okay, that makes sense.
Yeah, so that's your slope. And your intercept or your x intercept is T naught. So you can basically draw that. So, if I give a problem like this in any form, I hope some of you have a ruler, but I don't know how you would draw, but I'll think about it because it's all online. So now I have to figure out how you can make a line on your screen to see what the where it intersects. Oh, it's such a pain. But I don't know. I'll figure that out, tonight. But yeah, so now you see what I mean. Okay, let us do the screen sharing and let's begin. I realized that, where's my Scribble? Oh, what am I sharing? That's not what I meant. I can just share this screen. And I'm gonna put a correction to homework 6.2 that thankfully two students challenged me yesterday, which was nice. And I realized what my error was, and I'm gonna put a correction for that. It's a nice thing that they spent so much time and energy to figure out what was actually going on. But it's quite nice how they solved it. I'm gonna put their solution, my solution. It gives the same answers, but there's different ways to solve. So that was really nice. Okay. So this is an exam 2 review. Exam 3 review. Okay, what you should expect to know. So we're covering lectures 311 to 4.1. Okay, this is 6 lectures. So it covers multiple reactions in isothermal reactors. We're gonna talk about multiple reactions with heat effects, and it's just a bigger mess, but it's not that more complicated. And it covers adiabatic operation with single reactions. Okay. Now, multiple reactions, from my experience, is what trips up the students the most, besides reaction mechanisms. That's what I've been told. And we're going to try and clarify those. Let's look at first parallel reactions that happen in an isothermal reactor. So remember, we have 3 types of reactions. There are parallel ones, sequential ones or series ones, and mixed ones. But the mixed ones can be considered, part of them are parallel, part of them are series, depending on what the species you choose. Now, there is the one thing that you are trying to do as an engineer is to maximize the selectivity and or the conversion when towards the species that you wish to produce. So that is what you're trying to do. Now, you can look at parallel reactions and make qualitative decisions. So basically, you can first look at a qualitative analysis. You can do a qualitative analysis of parallel reactions. So for example, if you have, make sure I got, yeah, let's choose this one. Yeah. If you have 2 reactions in parallel, it could be more than 2. Right, this is just 2 parallel reactions. And you're given RD, says KD, CA, alpha 1, and CB, alpha 2, and RU is KU, CA, alpha 2, CB, beta 2. This is beta 1. Right? And you can also be given KD as in this way. Right? And then KU, where A is a pre-exponential factor. This is a number that's empirically determined. It's usually a very, very large number. That's empirically determined. Okay, so you have these, oh, this is EU. Okay, so you can be given this information. So the questions you can ask yourself is, if you want to maximize, say, D with respect to U, what kind of reactor would you choose? What temperature would you run the reaction at? What concentration would you feed A and B? So these are the questions you can ask. And you can qualitatively sort of assess what conditions to run your reaction. The one thing to know is that maximizing, this is a conceptual thing, but you should understand that maximize the instantaneous selectivity, which in this case is RD over RU. One thing that I didn't put here is we always multiply by the stoichiometry. Okay, but now it's 1, so it's RD over RU. That's in the book. So keeping in mind that in the book, the way we define selectivity and using the stoichiometry can be different from some of the other places you see it. But we're going to stick with the definition of the book, where, so if you have, so this is definition in the book. Selectivity of B over A is if you have a reaction of A goes to B and then another A goes to C, for example, is moles of B formed divided by moles of A reacted. And you normalize by the stoichiometry, right? This is the definition that's in that we use. And yeah, so you can do this and equate, oh no. So you'd have AD over AU of okay. All right, so this expression allows you to make decisions in a parallel reaction to maximize, say, selectivity of D with respect to U. One thing to keep in mind is maximizing the instantaneous selectivity, which is RD over RU, is the same as maximizing the overall selectivity of D over U, okay? If you remember this in a CSTR, these are the same. The selectivity at any point in the reactor is the same as the selectivity overall. But for a PFR, the selectivity across as you move through the reactor, it changes because the reaction happens as you move down the reactor. And we can actually write this in mathematical terms, but we'll do that in a second. Before this, I want to make sure we can do a couple of assessments. So in this example here, if, for example, ED is higher than EU, meaning that the rate constant for D formation goes up faster with temperature compared to the one with U formation. So if ED is higher than EU, you should operate at a high temperature, high as possible. Right, so that's what this means. So you could form D faster at higher temperature than you would form U. And if, for example, alpha 1 is greater than alpha 2, you would run at high CA. And what that means is equivalent to you doing your reaction in a PFR, because in the PFR, the concentrations are kept higher along the reaction, along the reactor volume. Whereas with CSTR, as soon as so you can graph it this way. So with CSTR, if you have CA not going in, as soon as it hits this, it becomes CA at this point. And that basically meaning that your rate is evaluated at a lower concentration than CA naught. But with a PFR, so if you have CA naught here, it starts there and it's gonna go down along the reactor length. So that means at any point in time, except at the very exit, the concentration of A is higher in a PFR than a CSTR. So if alpha 1 is greater than alpha 2, the selectivity tells you that you need to run at a high concentration of A and that you use a PFR. But then if you also have alpha beta, if you have beta 1 but is less than beta 2, then you want to keep the concentration of B low. So you can do that either by just feeding B at a low concentration, or you can do that by doing a semi-batch reactor where you feed B over time. Or you can do a system where you have multiple, you can have a series of PFRs with each one has a little bit of B added. You can have a series CSTR as well, but small CSTRs where you add a little bit of B between each reactor. So there is always a reason to do these things. You know, it depends on your economics. Depend if you have more than those two reactions occurring. It could also depend on heat of reaction. So if your reaction is highly exothermic or highly endothermic, then doing high conversion means it runs too hot, so you can do series of reactors, but each reactor gets a little bit of B, right? So you can have these systems, and you can cool it in between. So that's another kind of reasoning to doing interstage cooling, but not with equilibrium reaction. That's just a normal quality of life issue, where if your reaction produces way too much heat and that is not unsafe, so you could do smaller conversion, but multiple reactors with cooling in between. So that,
you explain the two lines you wrote above the drawing where it's like if ED is greater than EU. I'm just kind of confused on what it says. It's like operate at highest possible.
Yeah, so this. So if your desired selectivity is for D, so what this means is that at a higher, if the activation energy for formation of D is higher than formation of U. So that means at high temperature, KD is gonna be higher than KU. That's what this means. So at high temperature, you're gonna have, so if you have your KD times CA alpha 1, CB beta 1. So at high temperature, KD is higher than KU. So that means you form D more than U. Does that make sense?
So are you saying to operate at highest possible temperature or highest possible?
Oh, what did I do? Yes, that's what I meant to say. I think my brain went and said it, but my mind did not write it. Yes, so operate at high participal temperature. And then, if you have alpha 1, good alpha, you operate at high CA, which means you would prefer a PFR. If beta 1 is less than beta 2, in this case, you would have a system where CB is kept low, right? And we talked about some reactors you can use. Another reactor we didn't go over,
Yeah, can you go over why like running at a high CA is preferred using a PFR compared to just increasing the concentration in a CSTR?
Well, you have two concepts here. One of them is selectivity, the other one is conversion. So you could, so if your CSTR, no matter what, so if you are, let's say you operate your CSTR, you have a large CSTR with a high concentration of A, where you evaluate your rate is at the exit concentration of A.
Yeah.
Right. So you could have a CSTR where the conversion is low.
Okay.
But now you'd have to have a series of CSTRs, each of them with low conversion, right? And if you put a ton of CSTR with low conversion next to each other, you basically make a PFR. You know, by you just kind of integrating under the rate expression.
Okay. Got it.
Yeah. So yeah, so this is sort of the qualitative things that you've kind of we looked at for parallel reactions. One thing to note here, and it's not something that you'll be asked or anything, but you note that you can have both high conversion and high selectivity in parallel reactions. You can do that because the reactions happening, they're not connected, right? They're only connected by A, but the D and U, you can actually have complete conversion of A. A could be completely gone, but your selectivity for D over U is kept at a high high number if you choose the right conditions. So it's just a conceptual thing that you can think about. So now time and space-time are not the determining factors in your choice.
I have a,
Mhm.
oh, sorry. I had another question.
Go ahead.
Yeah, so for this example, what would the equation be for the overall selectivity of D with respect to U?
Well, overall selectivity is this equation, is this one here.
Yeah, so how would you go about plugging in actual variables into that?
Well, we're gonna get to that at the end, but since you asked, you know, there is so we solve I think we solved two different kinds of problems in the course in this particular in this section. So we solved the problem where, if you remember the Trem-Booz reaction. So if we're gonna look at that quickly again, but we solved the problem where you're asked to maximize selectivity.
Right.
And that's one. In this problem, to solve it, you just have to calculate. So if you have to we're gonna do it again in a few minutes, but I can already put that here for you so you can see. So if you write S of D over U, which is RD over RU, is, you know, KD. Oh, I'm not gonna write the energy. So let's just do KD CA. Let's say this is CACB, right? Let's say CA squared CA. And KU, RU is CU, KU CA CB squared. And this is KD over KU CA CB to the -1, right?
Yeah.
That's your selectivity. So what you can do is, if you're asked to maximize that selectivity, or no, if you're asked to, well, in effect, you're maximizing it. But if you're asked, what's the maximum concentration of D, so max CD, can you obtain in a CSTR? Max CD in a CSTR. So this is concentration. This is not flow, right?
Yeah.
So, okay. So max CD in a CSTR. So you can say CSTR S hat, which is of D over U, is the same as S of D over U. And S, question? And this is point or instantaneous. This is overall. And that is CD minus CD naught over CU minus CU naught. So that's what this is equal to. Right now, if this is both are products, so this is 0 and this is 0. So both are products. And then this is equal to this guy. You see that? So now,
Oh, so that's the equation for the overall selectivity, the CD minus
yeah,
CD naught.
that's the one.
Okay, okay.
So now you can solve for CD. So CD is CU times KD over KU CA CB to the minus 1. Now you can take, if you want to maximize this, you can do DCB DC. Oh, I guess what did I do here? DCA. Now you would use Stoic table to express CB in terms of CA, right? So you would use a stoichiometric table to do that. Now, and then you can basically do, if DCB, DCA equals 0, then you can calculate CA at which CD, this is D, is max. Does that make sense?
Yeah.
Yeah.
So that's like the general equation for the overall selectivity. It's like
Yeah, this is the one.
final over or minus initial concentration.
Okay. Here we write it in terms of two products, right? But you can write it in terms of if you have S overall selectivity of D over A, right? So it's gonna be CD minus CD naught over CA naught minus CA. Or we can, so once again, I'm gonna write it in the CA minus CA naught. See, this number is negative, right? But remember, we always multiply by this, and that makes it a positive number now.
Okay, so you always multiply the numerator by negative.
Yeah, that's the formula in the book. Can't remember exactly how that came about, why it's minus nu A, but it is minus nu A, and that makes it into a positive number.
Is that because A is a reactant?
It is a reactant.
Okay, so what if it was selectivity of like D with respect to U, like you were saying before?
Yeah, so
there would be no negative.
There would be no negative. Yeah, I think we went through this a few lectures ago. I think we did. I was realizing as we were I was realizing as I was trying to make that review that we actually went through a lot of things. Yes, go ahead, ask again. What was your question?
Oh no, that makes perfect sense now. I just wanted to clarify some of that.
Yeah. Yeah, we're gonna go through that in a moment too. Just since you asked, I wanted to put that out here. But for some of you, we're kind of waiting more of a structured way. We'll look at this again in a moment.
Thank you.
Okay. Now, talking about structured way, the one thing I did that wasn't so structured was I started from the wrong spot. Now, at the very, very beginning, when we talked about multiple reactions, we introduced the term selectivity and yield. So we introduced those two terms and we wrote our definitions. Now we just wrote the ones for selectivity. So I'll just do that again. So this is selectivity and yield, where, you know, if we have selectivity of B now with respect to A is moles of B formed divided by moles of A reacted. And we normalize using the Stoic coefficients. So this is what's in your book. And then we find that it's, you know, if we're looking at a CST or a PFR, it's FB minus FB naught over FA naught minus FA, right? So we use that negative sign to flip the order in the denominator, so that this whole thing is a positive number, because FB naught is often going to be 0. Now yield.
Dr. Denard, did you write FA naught twice?
I
Or was
did.
that supposed to be that? Or okay, thank you.
Yeah, I've done that many times. Okay, so yield is the same, is similar. Yield, moles of B formed divided by moles of A fed. So it's divided by FA naught. And then we, once again, we do our normalization. And what we found out is that yield over selectivity is actually equal to conversion for A. All right, so that's what we found out when we did some manipulations. And the one thing we did in class was we used those in a problem, and there are some problems at least that if you know 2 of these, of course, you can calculate the third one. So that's essentially how we, what kind of problems we did. So you can be given conversion, selectivity, and you asked to calculate yield of one species over another. So we did those problems, and these problems are cute. They are, you know, easy, and they could show up again for a few points on the exam. So that's it.
So what form would the yield equation take on for this example? Like
with this example?
Yeah, like with the A to B and A to C.
Yeah, so it's gonna be,
What would you actually plug in for?
it's just gonna be that.
Oh, okay.
Yeah, because it's just
and
moles
the
of,
FB you get from the Stoic table, right?
yes. Yeah, the FB is from the Stoic table. The stoichiometric table is always there. Sometimes we use it when we're solving reactor sizing problems, but it's always there because it's the equation.
Right.
Yeah, it's always there.
Thank you.
Also,
Alright.
When comparing yield of 2 products, how would like that work out? Is that possible?
It's not possible.
Okay, you can only compare selectivity of 2 products, but not yield.
Yes, you cannot compare yield of 2 products.
Got it.
Yeah, because by yield, you're meaning how much you're getting for how much you're putting in.
Okay.
So
yeah.
that's, yeah, otherwise you'd be dividing by 0. So that's really the definition.
Mm-hmm.
Some
Okay.
of you that are into, let's say, biochemical engineering, or that take like bioreactors, which we did not go over because of time, yield would be how much product you're getting from your cell-based reaction, how much you're getting per gram of glucose that you feed to your cells. That's a good definition of yield. Okay, so that sort of covers some of the qualitative aspects of our review. Now, the next kind of problem that we have been looking at, still with parallel reactions, because we'll talk about series reaction in a moment. The other kinds of problem is maximize selectivity, and I think one of you asked earlier, and I started opening up on that a little bit. Maximize selectivity calculate max product concentration. Oh, this is not writing. Uh-oh. I wonder if something's happened to my computer. Unique mass product concentration. Are people still there? I think, because my computer just did something strange.
Yeah, we're still here.
Okay, good. Because the screen just went black and I don't know what happened. Okay. So yeah, so that's another kind of problem you can be asked to solve. And it's still very strange, but let's see. In a certain reactor. Sorry, the writing is going to be strange for now because I'm no longer using the tablet mode. I'm just writing on the screen vertically. It's not the best. So it could be in a CSTR or PFR, right? What typically we dealt with liquid phase with these reactions. To make things simpler, I have actually tried to do a gas phase version. So in this case, let's say you still have, these. You can even have maybe another, you can have multiple reactions. Each of them have a rate. You can get minus RE1, minus RE2, minus RE3. You can see it like that. You can also see it as R1, R2, R3. Now, R1, R2, R3 are species independent. Now, if you remember from chapter 2, R1 is Ri over nu I. Right, if this is the first reaction, right? So it's going to be RA1 over mu A1. So you can see it, the rate being given to you in different ways. So you should be able to convert them, interchangeably. You should be able to do that. So okay, so what were we doing? Let's see, where's my, okay, there you go. Now, to maximize the selectivity, we talked about before conceptually, maximizing point selectivity is the same as leads to a maximized overall selectivity in any reactor. That's what we said. So if you have a CSTR and you ask, let's say this is your selectivity, this is instantaneous, is equal to your overall. And remember, this is CD minus CD naught over CA naught minus CA, right? And this is your selectivity, is your rates. So it's going to be RD over RA, like this, minus RA, okay? So now let's say that, so let me just put I'm going to put 2 equations because I actually have an example that deals with 2 instead of 3. I put 3 there because I guess I was trying to show off, but anyway, yeah, let's say that minus R1 is K1 CA squared, R2 is K2 CA. Is that what I did? Or is that? Okay, well, it doesn't matter. So RD is K1 CA squared, and RA minus RA total is K1 CA squared plus K2 CA. So you can divide everything by CA. So it's K1 CA over K1 CA plus K2. Right? So what you see is that this is equal to that. Now you'd be given K1 and K2. Yes.
I'm confused on how you got the denominator. You did KA or CA minus CA total, or what did you say?
This is RA. This is the total R. This is how much, this is the net rate of A consumption. Right? So A is being consumed in reaction 1 and 2.
Oh, okay. I see what you did there.
Yeah. So this is just the right-hand side. The left-hand side hasn't changed at all. This is just the right-hand side. Yeah. So now you know, if you assume that CD is 0 at the beginning, CD naught is 0. So then CD is CA naught minus CA times this guy. This is a function. This is just a function. And if you want to know the maximum CD, you just take the derivative of this function and equal it to 0. So max CD is just DCD DCA equals 0. And that will give you an optimal CA, which then gives you, when you plug it in, gives you max CD. So you know how much CD you can make maximum in a CSTR. See, that doesn't have the CSTR size, not really. You can just know how much CD you can make. Okay. Now, there's a small difference for PFR because the point selectivity is not equal to the instantaneous selectivity. So for PFR, the overall selectivity, and we did this graphically, so I'm not going to go through that again because it took us some time. Once again, we have CD minus CD naught. This is and that's equal to the averaged instantaneous selectivity. DCA. Right, and we are going from CA to CA naught, and then divided by the limits, right? So this is overall selectivity in a PFR. It's basically saying, we did this graphically once where we graphed instantaneous selectivity as a function of CA or something like that. I don't remember exactly what it looked like. And the selectivity, for example, say look like this. And this is where you're starting at CA naught. And then you're ending here at CA. Or, well, let's say this is where you're starting at CA naught. I'm gonna make this cleaner. So you're starting here at CA naught, right? Now to have the maximum amount of D, this is the area under the curve. So that means CA is equal to 0. So you convert all of it to maximize the amount of D that you're making. But the selectivity at which this PFR is operating is an average somewhere in the middle here. It's operating at some average selectivity. So that's what we showed graphically in your notes in the past. Yeah, so now if you look at this equation, you find out that you can cancel the denominators, and now CD naught is 0. So you find out that CD is actually just the integral from CA to CA naught of the instantaneous selectivity. And this is exactly what this graph is telling you. It's just the area under the curve. So Yeah, so then you can calculate the maximum amount of CD. The reason why it's a maximum amount of CD because you're depleting all of CA, right? You're going all the way to 0. That's how much. That's how you can get the maximum amount of CD in a PFR. So we went through that, and I cannot say that whether or not there will be a problem like this on your exam, but it's free. It's free for all. I mean, it's fair game, right? It's now you can, knowing CD. We did this in class. In any of these, you can calculate the space-time, right? Knowing CD, you can calculate space-time. It's essentially reactor sizing without knowing the actual volume. You just know the space-time, V over V, large V over small v.
How would you get that from?
Yeah, this is just like this is liquid phase, right? So for
Right.
for CSTR, you can write tau. I believe is this, right? So remember that for CSTR, we calculated CA.
Yeah.
Yeah. So you can size a reactor for a CSTR.
Oh, I see.
Yeah. You can
So for a
just know.
PFR, it would be different. It would be just
Well,
like according to that design equation.
The PFR is just gonna be dCA d tau equals minus RA.
Okay.
And you can do the same thing. But remember here, you're going CA, you're integrating from 0 to CA naught. Yeah, you can size a reactor the exact same way.
Okay. Also, for your expression for CD, oh, you cancel out the CD not because you're assuming there's none.
Yeah,
Okay.
you're assuming there isn't much of it at the beginning. Or there is none. There is none of it at the beginning. What am I saying?
Yeah.
Because it's the product.
Okay.
Yeah. So yeah, so you can use these. If the question is maximizing selectivity, you can do approaches like this to calculate your space-time and concentrations. Works really well for liquid phase. For gas phase, it becomes problematic because you need a volumetric flow rate. And it just becomes messy. Okay.
One quick question for you.
Yeah.
Where you wrote like up above, I see your equation for CD for the CSTR, but how do you actually solve for CA from that?
Now, this is what I mean. Like if you take the derivative of this equation, you can equate to 0 and you'll get
Oh,
CA.
so you say the left side 0 and then solve for, okay.
Yeah, yeah. That's how you would know what the optimum CA would be. That would give you the maximum CD.
Gotcha. I follow it now.
Mm-hmm.
All right, thank you.
So that leads us to the third kind of problem, where it's not about maximizing selectivity, it's about calculating it from a set of data. This is the problems that are solved in the book, right? So this is your chapter. Then from there, I like these because it really kind of gives you an idea, and I hope it does give you an idea of sizing, reactor sizing differences, and I hope that I test you on it, but I'm not 100% sure. So the idea would be, depending on the selectivity curve, which is that guy here, it can look different ways, right? So depending on how it looks, it kind of tells you what kind of reactor you would choose to run these reactions in. So it's essentially very much back to the first question is, you want to maximize selectivity. How do you do it, and what kind of reactor would give you that highest selectivity? Depending on how this looks. And how this looks depends on how this looks. See? So you can do that. It's unfortunate, however, that many of these are difficult to solve by hand, so I can't put something funky. The Trembouze reaction is the simplest, most straightforward version, and that's what people like to give as an example, that you can actually do it by hand because it's easy to actually integrate or work with. But some of the others are just complicated. Because trust me, I tried to develop a problem for last spring. I gave up eventually because I could never find something that I could easily solve, that students could easily solve for that, like integrating this S. Yeah. Okay. Now, where are we? We are. Dun, 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 dun. Yeah, so before we talk about the reaction, the problems that ask you to solve for selectivity, let us take a quick moment. And no, let's take a break first. Let's take a break for 5 minutes, and then we'll come back and finish our review. Let's resume. Yeah, so before we go talk about the third kind of problems to solve, which is calculating selectivity, set of stoichiometric table, we'll do a quick vignette on reactors and reactions in series. They are in fact simpler, even if you might not think they are, but they are in fact simpler to understand. The one thing that gets thrown at in them is the integration factor usage. That's the one thing that gets thrown at in this analysis. And I set up I sent a link yesterday how to use the integration factor, and it does a pretty good job going through them. So you guys can go through that. Yeah. I actually set up an example that also goes through it in detail versus the last time I just said, you should know how to do this. And then I think that many folks didn't catch that. Yay, you should look into how to do this. Okay, so say we can look at a simple kind of elementary reaction that in series where, let's say, R is your desired product. Now, you can have versions like this. There are versions that you cannot solve by hand easily. So something like that was on the homework. That's kind of difficult to do by hand. But there could be a simpler one, and that's in one of the problems in the book. Oh, yeah, that's fine. Oh, what am I saying? This is R. Completely screwed up here. Turn myself around. Yeah. So you could have this, this would be that. Right? You could have things like that. And that's fine. And the rate equations, right? So you could have, for example, minus RA. In this case, if elementary is K1CA and then RS is K2CR. In this case, RR is K1CA minus K2CR, right? You can have things like this, but you could also have a system where RS is just K2. It's zero order. That can happen. You should be able to solve any of them. These might be very difficult to solve by hand. It's possible. It's just difficult. You have to keep track of lots of things. But yeah, so something like this would be something we look. It's in the book. We looked at it already. And you could have a system where you have RS equal K2, and then minus RA is, in this case, K1CA minus K2CR, right? And RR is K1CA minus K2CR minus K2, or minus K minus 1. So you see, you guys should correct me when I'm messing up. Yeah, this is fine, but I was messing this one up. K minus 1, K minus 1, K2. And you could have a thing like this, and that you can actually solve as well using kind of integration factor approach. Now, one thing we can look at, so I'm going to do a problem where we actually go through the integration factor usage. And that way you can be clear of how actually it's used, even though the link is pretty good as well. So we can look at, to do this, we can look at a series reaction in a batch reactor. I trust that you can do this analysis in the CSTR because it's purely algebraic. Now, here's the goal here, once again, is to maximize some selectivity, say of R, a concentration of R maximized. Here, the one thing you need to know is that maximizing selectivity and maximizing conversion are not in the same, what's the word? They can be antithetical. They're opposite, meaning that your concentration of R that is optimum or maximized will not happen at the highest conversion of A, because the reaction is eventually going to go to S. That's the end product. So you have to stop the reaction at a certain point to get the maximum concentration of R. So that's the difference here between that and parallel reactions. In parallel reaction, you could, in principle, run the reaction where A is completely depleted, but you've set up your reactor in a way that maximizes your desired product. Here, however, if A is completely depleted and you let the reaction go long enough, you're gonna make S. So that's now time and space-time becomes important factors in your calculation and in your choices. Okay, and now the reaction rate constants also become a factor. So your K1 and your K2 becomes a factor. For example, if K2 is much, much bigger than K1, that means one of the things you have to do is run the reaction at very low conversions. Because if you let it go any long, it just goes into S. You know, so that's sort of the choices that are different between your series and your parallel reactions. If you have mixed reactions, then you have both choices to take into account. So yeah, that's my 2 cents there, the kind of a conceptual thing to think about.
Why is RS just equal to K2?
Because that's the reaction. This is this reaction.
Like it wouldn't be K2CR?
Oh, I'm telling you that you could have a case where the formation of S is not dependent on the concentration of R.
Oh, I see.
Yeah, you could have a case like that.
Oh, you would have to specify that, right?
Yeah, I would tell you, yeah.
Okay.
I would say something like, this is a series reaction, and these are the rate expressions for each reaction. Calculate the concentration of your desired product, say R, as a function of A. So the one thing to keep in mind here is that Ca naught, again, we do this in liquid phase for that demonstration, is equal to Ca plus Cr plus Cs, no conservation of mass. So, you know, so one thing you can do, and this is the one thing you know Ca naught. Your goal is to express these concentration as a function of Ca naught. And that's how you can solve for their profile over time or over space-time. Does that make sense? So that's really the goal. Say that again?
I was just saying, yeah, that makes sense.
Yeah. So that's the goal. The goal is that you have one thing that you know. Can you express the others in terms of that? And that will give you, in each case, a function that is a function of how these concentrations change over time or over space-time. So that's really the goal of those reactions in series. Okay, now in a problem that we're going to talk about in a minute, the space-time is given to you, for example, then you'd plug that in and then you'd get all the profiles, you know. Anyway, so let's go through that quickly. I think we want to make sure we go through all of the different things I want to, you know, test you on. All right, so if you look at a mole balance on A in a batch reactor, and this is liquid phase, is just equal to that. Actually, no, it's not equal to that. It's just equal to RA. And RA is minus K1CA. Okay, this is your design equation for a liquid phase batch reactor. And if you solve this, integrate it, so you have dCA over CA equals minus K1 dt, and you integrate from CA naught to CA, right? And you integrate from 0 to T, you'll get log of CA over CA naught equals minus K1T. Then you can say CA is CA naught e to the minus K1T, right? So that is known. You can plot that. It's just going to be exponential decay. So that's what's happening to A. Now, what is happening to R? And this is the thing that is different here. And this is how much R is made versus how much R is depleted. And then this is where the integration factor usage comes in, because this takes the form of dy dx plus p of x times y equals q of x. Right, now x is CA, so you can see this is a function of x. This is not a function of x. I mean, it's just a constant, right? That's all it is. It's a constant. So the integration factor to solve this problem is e to the integral of px dx. And that's e to the integral of k2 dt. And that's e to the k2 t. And what you do is you multiply both sides by both sides of your equation by this. Remember that now CA is CA naught e to the minus K1T. That's what it is. So it's K1 CA naught e to the minus K2 minus K1T. Okay, that's just what that is. Now, the one thing to keep in mind here is that if you expand this, you're gonna get e to the K2T dCr dt plus K2 e to the K2T CR. What you should notice here is that this is y times dx dt plus x times dy dt, right? So if you take the derivative of e to the K2t, is K2 times e to the K2t. And this is that's the form it takes. And this is not, this x and this x are not related. This is just like, algebraic form. And this is equal to the product xy, right? So this thing is equal to d dt of e k2 tcr. And that's equal to k1 ca naught e to the k2 minus k1t. So this is where you are. You can integrate both sides. So you're gonna integrate both sides. So you're gonna swing that dt over here. So you can integrate right? So you can basically do this integration. Here you integrate from 0 to t. You integrate from CR naught to CR. right? So you can do that integration. And you can, this integration essentially is e to the k2t. Oh, I put a minus here, should not. This side is just e to the k2t CR. And this is from CR naught to CR. And this is K1 divided by K2 minus K1. Well, I guess there's a minus, so it's K1. Is it K1 minus K2? Can't remember. You can correct me later if I made a mistake in my integrating of exponentials. Yep. So now when you integrate this, if CR naught is 0, so your initial conditions are at t equals 0, CR naught equals 0. So these are your initial conditions. So that means if you when you plug this in, it is e to the k2t CR minus e to the k2 times 0 CR naught. Yeah, so that's the left side. And here you evaluate from 0 to t, so that's k1 CA naught. Please double check that I didn't mess this up. And this is e to the minus 1. Right? Because if you put e to the 0, that's 1, so that's minus 1. So this term cancels out. You can now solve for CR if you divide both sides by e to the k2t. So that ultimately gives you I think I did mess up because I think it's supposed to be to the minus k1t. Ah, I know what I did wrong. There was no minus sign here ever. Yes. Yeah, from there. I put it in accidentally. Yeah, that makes sense. That works. So then yes, you're left with minus k1t because okay. You can remove that one too. Okay, that's that. So that's how you use the integration factor to solve this ODE.
One quick question. When you remove the negative sign, does that change the denominator, like the k1 minus k2, or does that stay the same?
That's a good question. I think it stays the same. Let me check in the book if I didn't mess up. I don't think I did though. I think it's still, I think it's fine. But you guys are younger than me. You should have remembered all your math. Let me see. Oh, maybe I did mess it up. I somehow did mess it up. It's supposed to be K1 over K2 minus K1. Let me see where I screwed up. Oh, well, yeah. Yes, that makes sense because I'm dividing by it. Yeah, it's K2 minus K1.
We lost your screen. We can't see your
Yes,
scribble.
that's right. That's what I accidentally pushed on it with my fat fingers. Hold on. Yeah, So this is why. It's because you're dividing by it. Okay, I think we are good. No, not quite. Okay, we'll change it here too. Okay, so that's how you use it. It comes in handy. And now the third kind of problem. So this problem here, we can know how R and S and A are changing over time in a batch reactor. We can know that. And there's problems in your book, and there's also solutions of those problems that go through this. And if you're asked, for example, what's the mole fraction of each species leaving the reactor at time, 3 hours, you can solve for those. And for CSTRs, these are algebraic. You basically do, you use the design equation for a CSTR to solve for CR, and then you also know what CA was. You plug CA in CR. We did this before when we were looking at reactors, CSTRs in series, for example. It was a similar process. And in the class, we went through, for example, what's the maximum concentration of R? It's the same idea. You take the derivative of this equal to 0, you'd get the optimum time, the optimum reaction. Concentration of R is a similar thing. So we won't go through that, for time, but that's the idea. So you can solve problems like this if you can derive these expressions. So you have CR, you have CA, somewhere up here, right? And then of course CS is CA naught minus CR minus CA. So that way you can solve for CS pretty easily. And and then you can have that profile. So you can plot this and find the different expressions. Now the third one, which has to do with the question I was asked about choice. So the third kind of question is to calculate, say, extent of reaction, reactor volume, when you have multiple reactions happening in a CSTR, PFR, or batch. So say you have reaction like this happening, and you're given an R1, and then you have this craziness occurring here. You give an R2. This is a mixed parallel. This is a mixed parallel. So for C, it's a series. For A, is parallel. So it's a mixed series parallel reaction. Now, the first thing you do is so let's say you're asked to calculate molar flow rate out for D, or calculate selectivity for C over D, or calculate the volume that would give you a certain concentration or a certain selectivity, which we haven't solved that way, but I imagine that's also possible to do. So yeah, so that's kind of the third kind of problem. Now what you do is you choose your basis. So the first thing you have to choose basis, but what I mean is actually not basis, variable you will use to set up problem. So that's the first thing you do. Now, because it's multiple reactions, makes the series parallel. One thing you can do is to use extent of reaction, eta. So eta 1 and eta 2. So you can use those. And when you do that, your Stoic table is written in terms of that. So the Stoic table is going to have, say, A, B, C, D, and even an inert. If this is gas phase, it will work out the same. So you'll put on the FA naught, FB naught, and let's say there's no C, there's no D, and this is an FI naught. And here you'll have an FA naught minus eta 1 minus eta 2, right? Because A is in both is being depleted in both reactions. And eta is the extent of reaction. And FB naught, FB is just FB naught minus eta 1. Now FC, there is no C in, FC is gonna be 2 times eta 1 minus eta 2. Yeah. And then FD is eta 2. And then you can do the, total, blah, blah, blah. So you can have that. So this is what your Stoic table is gonna look like if you choose your variables to be eta 1 and eta 2. Now the next question is, you have 2 variables, you need 2 mole balances. So you don't need a mole balance on each species. You just need 2 mole balances. The question is, which 2 do you choose? Now, for ease of solution, I would choose mole balance on B because it appears in one of the reactions only, and I would choose a mole balance on D. So that's what I would do if I'm choosing eta.
Wait, how do you know that you need 2 mole balances?
Because you have 2 variables. You need 2 equations. Yeah, you need 2 equations. So that's how you would set it up if you're gonna do it in terms of eta. Now that mole balance depends if you have a PFR or a CSTR. So the mole balance in terms of eta can be derived from the general mole balance, right? So if you have, if you take let's take a PFR, for example. The general mole balance is DFB dV equals RB, right? That's the general mole balance. FB, you can just put FB naught minus eta 1 over dV equals RB. And FB naught is constant, so you would end up with minus d eta 1 dV equals RB. You see? So now you have your differential equation in terms of eta 1. And RB here, I don't know, I didn't give the things. But I guess RB is minus R1. So that cancels the negative signs. So yeah, so you can solve that. Now you're gonna end up putting both. So if you do it on D, it's gonna be again DFD dV equals RD, right? So it's gonna be D eta 2 dV equals RD. Right, and RD is R2. So you have 2 differential equations. And your initial conditions, the reason I like this a lot is because your initial conditions is eta 1 equals eta 2 equals 0. So I like that. You don't need to know what your, what your starting concentration is or anything like that. Well, you need to know it to put it in the Stoic table, right? Well, you need to know it, but at least to set up, it makes it simple. Now, if it's a CSTR, you set up, with the CSTR design equation, but with a CSTR, you can do this using solver because you have 2 algebraic equations. Like you have 2 ODEs, but if you do a CSTR design equation, where is V equals FA minus over minus R, well, let's say FI. Let's do FI. So I think that's what it looks like, right? You can once again plug FI as this. So let's see what happens. If you do it on B, you get FB naught minus eta 1 minus FB naught over minus RB. And again, it gives you minus eta 1 over minus R1. You see? So you end up with, and you can do the same for the other guy. So you get 2 algebraic equations. I may have this wrong. Make sure I don't. I often do. Let's see. Bum, 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 bum. Yeah, I did have it wrong. So it's Fi naught minus Fi over minus Ri. It will give you the same answer. Yeah.
Also, why did you choose to do it instead of eta and compared to like x, or like keeping it in terms of just?
Yes,
F?
we're gonna get to that just now. So
Oh.
we choose that in terms of eta. I explained it that to me it looks simple to do, right? You can do it in terms of F. So let's just do flow rates. Now your stoic table is just gonna be flow rates. So if you have A, B, C, D, and then I, Fa naught, Fb naught, 0, 0, Fi naught, and then out, Fa, Fb, Fc, Fd, Fi naught. And your mole balance, your mole balance, your design equation, say for PFR, is gonna be dFA dV equals Ra, which is the net Ra. So so it's gonna be net Ra. And here net Ra is minus R1 minus R2. Now here's what happens when you do this in terms of flow. You have to write a mole balance for each species, except the inert, because the inert is not changing. So you have to write, I believe that's that. Right, 2R1 minus R2, and the FD/dV is R2. Now your R2 or R1 is gonna be some like K CA. Let's say it's K1 CA, right? So let's say this is gas phase. So that would basically be the reason why you would want to do that, right? This is gas phase, because if this is liquid phase, everything becomes concentration. Does that make sense? If it's liquid phase, it can become concentration. But let's say gas phase, so this would be K1 Fa over V. So that V would come from here. Right, say there's no pressure change or temperature change. Right, so this is what your exam is gonna look like. Okay.
So you're
gonna-
saying,
Mm-hmm.
oh, sorry.
Go ahead.
So you're saying if it's liquid phase, we can just keep the rate laws in terms of concentrations, but if it's not, then we should convert it to.
Yeah, so for
mole.
example, if this is liquid phase, this dFA dV, you can write it as d Ca times V dV, right?
Yeah.
You can pull the V out. Oops. Yeah.
Yeah.
Yeah. You see now it becomes concentration.
Oh, because the V dot isn't.
The V is equal to V dot, V naught.
I see.
Yes. So that's where, if you're going to put it in terms of flow rates, if it's liquid phase, you're really putting it in terms of concentration, because the V you pull the V out. But it's your choice. You can actually do liquid phase in terms of flow rates. That's up to you, as long as it's consistent. Does that make sense?
Yeah.
Yeah, it's consistent, right? So now what you end up having to do is to put each of these to write them out. So your exam is going to ask you to do something like that, where it's going to go through the algorithm. If you choose to do this in terms of extent of reaction, first write out the Stoic table for each. Then write out the rate for each species. Then take the net rate and plug in from stoichiometry what the net rate becomes, right? So in Python, you would define R1, you would define R2, you would define each thing. So that's what you're doing. And then you'd have a system of algebraic expressions and a system of differential equations. If you're doing PFR, then you'd plug them in. And that's how I can ask you things on the exam that I know that you understand it. So that, yeah, you don't need to plug in anything in Python to solve. You can just say, okay, and I can say, okay, if you do this correctly, you should get these numbers. And from these numbers, calculate, let's say, selectivity, yield, blah, 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 like these types of things, yeah? So, okay. Now we'll take, I think that sort of covers the multiple reactions, right? I'm hoping that it does.
Dr. Denard, can I ask 2 questions before
Yes.
we move on to the next one? So for gas, it's easier to use the concentration. No, for gas, it's easier to use the flow, and for liquid, it's easier to use the concentration. So when is the extent easier?
The extent works for both. It's just that the extent of reaction is easier. Oh, if we want to say what's easier, if this is what if we're talking about, because they're all, once you understand them, they're all easy. But if we really want to get down to what's easier to use, the extent of reaction is preferred if you have a CSTR where you're going to have algebraic equations, right? Because with the CSTR, you'll have 2 algebraic equations you can solve simultaneously.
Okay.
Right. Now, if you did this for CSTR, so let's see what would happen for this. If you did flow with CSTR, you'd have V equals FA naught minus FA over minus RA. So this is net. And then you have V equals FB. So you'd have a bunch of equations that you need to solve at the same time to satisfy the volume being the same, right?
Okay.
That's what you'd have to do for CSTR, but we actually never did that because I think that seems a little bit silly. You set up 4 different ones and then you say volume has to be equal by changing FA, FB, FC, FD. That's what you'd ask solver to do. Yeah, that's what you'd have to ask solver to do for CSTR. But if you use ADAS, go ahead.
For the flow rate one, you knew to have a mole balance for each species because why?
Because you have an unknown. Each flow rate is unknown.
Okay, because in the out column, because those are all like
yeah, the out column. The only thing that you actually know in the out column is the inert, right?
Okay.
So you don't know anything from the others. So that's why you'd have an equation for each. So that's each of your unknown.
So if you were doing it in CA, you would still have the mole balance for each species?
Uh-huh. If you're doing in CA, you'd still have the mole balance for each species, but it would just be in terms of CA because it's liquid phase. Exactly. This is why when if we think of what's easier, I don't think it's the right way to say it, because with ADA, you have to do some algebra, right? And that can trip you up. Whereas if you're gonna just list the different mole balances, you don't really do any sort of you're not doing any crazy algebra. You're not doing any algebra, you're just listing them. So I don't know, easy is relative there, right? So
also in terms of conversion and extent, are they basically can be used interchangeably?
No.
Benefits of one over the other.
When you have multiple reactions, do not use XA.
Okay.
Do not. The only way, the only place you can use XA in this example is on X. You can use it on A because it's a reactant and it's being converted, right?
Yeah.
But you don't know how much A is going to C and how much A is going to D. You just know how much A has been depleted. If you try to use conversion on C, you'll run into a big problem of dividing by 0 at some point, because it's a product and a reactant at the same time. So you can't use conversion. And the rule of thumb is don't. You could use conversion on A, it would work, but you wouldn't know your selectivity. You would just know how much. For example, you could size a reactor. If I tell you 90% of A is depleted, you can tell me how big the reactor is. But you can't say, and this is isothermal, remember, isothermal. Because if this reaction has heat effects where reaction 1 has different heat requirements than reaction 2, well, you can't tell me how big your reactor is at all, because heat becomes something that you have to take into account. But in any case, rule of thumb is if you have multiple reactions, either choose ADA. ADA seems to be easier if you're dealing with a CSTR, because you can solve it in Excel. You just have, if you have 2 equations, you have 2 extents, and you just have 2 unknowns. And then you can back calculate the flows from stoichiometry. Yeah, you can basically say if you have ADA 1 and ADA 2, you can calculate all your flows. If you're dealing with, say, a gas phase PFR, maybe it's better to calculate it in terms of flows instead of molar flow rates. But you can also use ADA for a gas phase reaction, because we did that in one of the examples, and I think I put that up in one of the Python things. I think I put that up. So you can do ADA for anything. It's fine. It's easy. It's straightforward. You don't have to think of different conversions and these kinds of things. So you can just do ADA for everything, really, if you're comfortable with it. So yeah, that's the approach. Does that answer your questions, guys? I hope it does.
Yep. Thank you.
Okay. Now we have only a few minutes, unfortunately. We introduced, so the exam will have a problem with adiabatic, and I posted the 2 things for Alex to work with you, so I can be comfortable asking you, for example, to solve for how how much heat is what's going to be the temperature of the reactor at the end of a reaction, what's going to be the conversion. Now, I'm going to go through this quickly, but I'm going to ask, I don't know if Alex is having another review tomorrow. Is he? Do we know?
Yeah, I think he just has his office hours.
Yeah, it's his office hours, but no review.
Okay, I'll send him an email to actually go over adiabatic operation for whoever shows up at the office hours. I would hope that.
I think he records it as well, or at least I'm going to ask him to, so it should be posted. Okay,
that's good. That solves the problem. So here is what we need to understand. We have, so this we're gonna look at adiabatic operation. So heat effects changes our choices for reactor sizing, and we've established that. And if we looked at our algorithm again, we know we have our mole balance, we have stoichiometry, we have rate laws, and now we have energy balance. We can have pressure drop in there, right? In between, but let's not put that in, for example. So these are the 2 things. When you have to combine all of this, so combine and evaluate. Wow. Okay. The new thing that's here is the energy balance, which we wrote it for flow systems, for flow reactors. we've written, for example, Q. I'm going to drop the shaft work because we never use it. Okay, that might look like a lot, but it's not, because what you're looking at is you have some heat that is coming from outside, either from a jacket or a coil or a heat exchanger. So you have some heat coming from outside. And you have a term here that is bring my reactants to the temperature of my reaction. Not just my reactants, bring the species at the inlet. So there could be an inert at the temperature where the reaction is going to occur. That's this term. This is just basically sensible heat. And this one is how much heat is generated by conversion of reactants to products. That's what this energy balance is, very simply. And this term taken together is the overall enthalpy change. That, because it's got heat of reaction at a specific temperature, at the temperature at which the reaction occurs, and the heat it takes to bring the reactants and other species to that temperature. So that's your overall heat. So that's pretty much what that is. And it's equal to 0 for flow because it's steady state. Okay, now adiabatic means Q equals 0. So that's adiabatic. That means, and let's say we have single reaction. So we have a single reaction, Q equals 0. That means we can solve for the temperature outside the reactor, which is just gonna be, in this case, it's just gonna be that. The one very important thing we do in the class is the assumption that the delta H of reaction is independent of temperature. When, for example, if you have a reaction if you just have A plus B goes to C plus D, you can have a system where delta Cp equals 0. Delta Cp is the stoichiometric summation of stoichiometric coefficient times Cp of each. That can be equal to 0 if the heat capacities of the species are very much the same. They can be very similar. Or you can have a term where delta Cp times T minus T reference is much, much less than delta H of reaction at a reference temperature. And in that case, the delta H of reaction does not change much with this increase in temperature. So we can then sub that for this. Okay. Now, what this does is for adiabatic operation, it has a relationship between your temperature of your reaction and the conversion. So that's the relationship that you're looking for. So if you think about what you've done, if you think about combining, so this is what we talked about. We're gonna take mole balance, stoichiometry, rate law, energy balance, and combine. So what this means is if you have a rate law that is KT CA, right? Now K, say it's A exponential of minus E over RT. CA, this is where you plug in this. So you plug that reaction in. So you see how this works? This is how in your mole balance, so this is your R, this is minus RA. this is how in your mole balance, say your mole balance, let's say for CSTR, you see now you've included the energy balance in your mole balance because you've replaced T with what T is as a function of conversion. And now you can solve for, let's say, a volume of your reactor that is operating adiabatically. You can solve for the temperature at which the reactor is operating because, say, I give you XA, so you know XA, so you can know T. So if you know XA, you can calculate T. You can plug T in, and you can solve for volume of your reactor with adiabatic operation. Conversely, if you're given the volume, you can solve for XA, but it's just more difficult to do because it's under an exponential, and it's also out here. If you remember, it's also out here. So that's something you'd have to do, let's say, with like, Excel or something like that. And it's even more complicated if it's a PFR. Now you have an integral that has, if you're integrating XA from 0 to XA, but XA is appearing in both under exponentials and outside of the exponential, that becomes something you have to use Python or some numerical solver to solve. Okay, so that's what, in the short few minutes that I had explaining what do you expect it to be able to do. What you expect it to be able to do is calculate your exit temperature given conversion under adiabatic operation. And that's essentially that. You're also expected to understand how this adiabatic temperature, how the temperature of your reaction changes, because this is a line. This is a straight line. This is XA, this is T. This is T naught. This is a straight line, and this is your slope. I guess the best way to do it, let me do this instead. This is XA, and this is T, and then it starts from 0, and then temperature goes up as XA goes up. So you have that, and this is your slope right here. This is your slope. So you can, but I guess it doesn't start from 0. So let me redraw this. It starts from some T naught that's over there. So this is your T naught. Okay, starts from some T naught. Okay, so you're expected to tell me, if I ask you, you can change the slope if you change this. You can change the slope if you change that. You can change the slope if you change, well, I suppose delta H of reaction we say is independent of temperature, so I guess that would be a constant in most cases, but you can change your slope by changing the flow rates. Okay, so you're expected to understand the equation. That's what I'm trying to say. All right, but anyway, it's almost 5. It's been a pleasure. I didn't think that we're gonna go through the whole time with the review, but I appreciated all the questions. And I was secretly hoping that's how the class had started out. But I think we still have 20 days, well, not 20 actually, about 15 days, 2 more weeks to really engage and make up for the lost time. Okay, any other questions? But because you guys are ready, right?
Quick question.
Yes.
Doctor. If you were to go back to your integration factor example, when you set like px to equal k2, what I didn't understand was like I didn't realize k2 was a function of time. I thought k2 was only dependent on temperature. So how?
No. What is k2 dt? The integral k2 dt. There's no time.
So, but like, doesn't px equal mean that that's a function of x? And in this case,
that's the general way, but it just happens to be a constant.
I see. Okay.
Right? I mean, px is just say, yeah, it's a function of x, but it's just a constant there. But I would ask that you look at page that's in Roberts, page 214 at the bottom. just look at that. Now you will see in this case that px is not a constant.
Okay.
Yeah, it just happens here to be a constant, so we just went with it.
Okay, I see.
Mhm.
Thank you.
I had another quick question. Like if you could go back to your final slide.
Let's see. Oh, there you go.
Okay. Yeah, so when you were saying if this delta Cp T minus Tr is much less than the delta H of reaction, does that just mean delta H isn't a function of time? I mean, of temperature?
Of temperature, exactly. This is why it can be, am I sharing still? Okay, I am. So that is why you see this term doesn't have to be a temperature function in it.
Okay, so you wouldn't need to use like the Arrhenius equation to get like a new delta H in that case.
Yeah, well, it would be the Ventov equation, I believe.
Oh, the vent, like the one that the
No. Let me take that back. This, if it is dependent on temperature, you'd have to calculate the delta H at the temperature of your reaction.
Okay, yeah, and that's that formula.
That's like, so at some point in the past we talked about delta H. Yeah, that's the formula.
Like the
that
reference temperature and everything.
Exactly. So you'd have to do that.
And is that something that would be specified in the problem? Like
well,
T minus TR is very small or something?
Well, I'm gonna say this. Now I don't think I'm gonna ask questions like this, but who knows? But I'm gonna say this. If your reaction is happening at 1,000 degrees C, and I give you a delta H of reaction at reference temperature, you should probably check it.
Yeah.
I mean, that's like, that's a lot of heat. That's pretty high temperature.
Right.
Yeah. But if I tell you delta Cp is 0, it doesn't matter what the temperature at which it's occurring. It's just gonna be delta H of reference, right?
Yeah.
Yeah.
I see.
No, good point. But this is your thermal coming back to haunt you. Hopefully not. So that's what I mean. Yeah, so this is this. If the temperature change is not very big, which you don't know at first, for example, right? Because you have to know it, calculate it. So there is a few things like, yeah, but there's not gonna be tricks, If the question is about calculating a new delta H, the question is about calculating a new delta H. It's not gonna be embedded within a bigger problem that you're like, oh, you guys did not calculate your delta H. Yeah, it's not gonna be embedded in a bigger issue, but it's important that you just understand why we use delta H of reaction at reference. That's why I did this. It's not because it's not a hint or whatever. It's just like, hey, this is why it's there. Understand that's why it's there.
That's what I'm saying. That makes sense.
Yeah.
Thank you.
And I've done it a bunch of times already now. I think I'm not gonna do it again. I'm just gonna say, okay, you guys know this now.
Yeah.
Okay. I think we're all set. I'll see you guys in 2 days.
Thank you.
Mm-hmm.